the memory in terms of the computing. So what is the main data structure of the memory management? That is the paging. So paging is what? Page is the fixed size of the memory. So we will. By the way, why do we need the memory? Memory is a storage, right? We try to keep the data and information. Mostly is the instruction because the modern computing architecture is based on the instruction set architecture. You probably heard about ISA or the instruction set or the instruction set architecture. The computer will be operated by processing such an instruction. Okay, so CPU, for example, CPU will read such an instruction data from the where? Register. Register is the small but very fast the storage. So the CPU can read such a data, instruction data from the register, but it's not enough. So at the time you need the memory. Okay, so using the address, sometimes such a memory address. Actually, the memory is nothing but the range of the address. So we have the 0 to low address format and the higher the maximum address format. We have a bunch of range of addressing. Okay, low to high. But when we have the bigger size and bigger size of the memory, what is the size of your memory on your laptop? This is sometimes 8 gigabytes nowadays. Okay. Then in real server and enterprise level server is sometimes terabyte. Okay, such a range to find the specific location of the memory to get the instruction information or the data from the memory, it takes some time. Also, if we use just the entire process or the segmentation, okay, but that causes something fragmentation issue. Even though we have the free space, but we cannot utilize such older space. To address that problem, we are using paging. Paging is a unit of the memory data structure. However, we have seen the management, the scheme to manage what? The bunch of the page. Suppose that when we have the 1 terabyte size, I never seen 1 terabyte size the memory, but 16 gigabyte, 32 gigabyte memory size, which is normal nowadays in the server side. Even workstation, you can purchase a workstation, $2,000. It's a 32 gigabyte memory. How many the pages do you have? Divided by 16 gigabyte divided by the 512 byte is huge. So to manage such a huge number of the pages, it takes a time. So mostly nowadays we use hierarchical approach. Okay, multi-level process. That is to find the specific page. But anyway, basically, the memory structure are based on the address. Okay. Then, so we have seen how to map between the process and the paging. In other words, process is what? It's actually the memory. Okay. Eventually, the program that you compiled, that you possess, that you copy, okay, from the Google Play or from the CD drive or sometimes online or the copy, whatever that is, that program eventually will be loaded into the memory. In other words, the program structure that you compile from your source code by using the compiler, that source code to the program is what? It's a memory. So we will consider such a program as the virtual memory. Eventually, that part of the program will be loaded into the memory. So why don't we make the same structure of the, why don't we make such a virtual memory, your program structure as the same as what? Your physical memory structure that we learned in the last class. That is the paging. Okay, so we have the bunch of page frame, number of frame. So we assign the page in your program virtual memory to the page frame in your physical memory. Then we need some in-between mapping table, that is memory management unit, MMU. So most of the current, especially for Intel architecture, they have such MMU unit in terms of hardware to speed up, because mapping is the critical to speed up your process. Okay, so today we are going to talk about how to manage such a virtual memory. Okay, so have you ever heard about the virtual memory before? Where?
In property, in some setting in the computer.
Yes.
Yeah.
If you go to the computer, my computer, and the property, you can actually set the size of the virtual memory. It was used for what? At the first time when we used the small size of the memory and the small size of memory, we use such a virtual memory as the swap space. Swap means what? In case there is no available space in the memory, we roll out all the process, all the logical, the virtual memory to the disk space. Then you can roll in, swap in your process that you want to learn. Okay? However, that takes a long time nowadays. Even we have the bigger size of the memory, we are not going to use such a virtual memory swap space as the really swap. Instead, you can go to the my computer and find I cannot remember the exact button, if it's system variable, somewhere. Let's try. So my computer, property is different. This device manager, I don't think so. Remote setting, system protection, advanced system setting, I guess. Performance, user profile. Yes, you can change your, because I have already seen, you can change the virtual memory over here. Okay, so advanced. Yes, right now virtual memory size is 200 megabytes. Okay, it was suggested when you install the Linux system long time ago, maybe 10 years ago, 15 years ago. So when you install the Linux system, the swap space is recommended by 1.5 times of your physical memory. Okay, because you'd better have the bigger size, the bigger than your physical size to swap out the program, entire processor is already in the memory. Right? Should be bigger than that. But nowadays, this one is used, so it's suggested. So if you want the better performance, you can have the still 1 or 2 times of your physical memory. It's set very small. It's good time to change it. So let me change the 2 gigabyte. But it's the maximum size is already 2 gigabytes, so I don't think I need to change it because it's a initial size. It can be up to the 2 gigabytes. That is the virtual memory. Then nowadays, such a virtual memory used for what? In terms of the data structure, it's the same as a physical memory. Okay. For example, we have the memory. It's a physical memory. It's divided by the pages, so we manage such a page frame number. Okay, sometimes it's hierarchy structure. But when we use the sum of the pages, okay, then for the program virtual memory, okay, we consider program as a virtual memory. So this one will be loaded, this one will be loaded. So why don't we keep this one in the hard disk drive, not the program level? Even though this is on the hard disk drive, we consider this one and this one is the same data structure. The only thing we need to consider is in and out page by page. This is the ideal current usage of the virtual memory. Sometimes it's called the swap space, but it is not longer used for swap in and out. Instead, it's a page in and out for virtual memory space. So virtual memory is in terms of data structure, it's the same as the memory, but it's located in the where? Hard disk drive, secondary storage. Okay, so it still need what? Physical input and output. So which means even though you increase such a virtual memory size up to the 1 terabyte, we cannot get the linearly increase the speed of. Okay, so it's not required to increase such a high. So that is the 1 or 2 times of your physical memory may be enough. Okay, so that is the virtual memory. We will see.
So, when
Yes.
instructions are working, how do they decide that they will go for using virtual memory or memory?
Okay, we will see first. So first one will be, so when you start your program will be loaded into the virtual memory, or sometimes it's on demand. Your program, only the first page will be loaded, then placed in your page frame. Okay? Then not all the pages will be loaded. Some of them will be used whenever they need. They will be copied. But from time to time, it's a full. Some of them should be page out. This is called the page out, or sometimes it's called the page fault. We will see detail. But this one will not be gone. Just copy to the virtual memory. Okay. So first time when you execute your program, the page will be loaded into the page frame, the physical memory, then in and out. We will see how to in and out. Because we have the anyway limited the page frame number, so we should have the smart way to utilize such a thing. So at the time, if we bring the page into the page frame, this is called page in. And if we bring out to the virtual memory, this is called page out. And also, so when you need the free pages, but there's no free page, that is called page fault. Okay, the more page fault you have, the less performance of your system is. So our goal is to minimize the number of page fault. Okay.
The main memory nowadays is bigger and bigger. Do you still need a virtual memory?
Think about I'd like to run my Java virtual machine with the 2 terabyte, the memory size, for example. Do you have the 2 terabyte memory size? No. So sometimes not only just the program size, okay, your program size may be the 10 megabyte, but in your program, the process program itself is a memory based. All the data will be first loaded into the memory. So you need more heap size or more stack size, bigger stack size. At the time, definitely you do not have such a size. Okay, how many processes you are running? Why don't you check your task manager? So you will see physically how many of them are used. Okay. So to address that problem, we try to use the physical and the hard disk drive for the memory area. Okay, that is called the virtual memory. Okay. So what is a virtual memory? It's from the physical memory we drive to what is a usual logical memory? It's a program. Okay, so we will use this part, the hard disk drive part, to it's kind of an extension of your physical memory. Okay, so that is the virtual memory. My battery can last only the 30 minutes. So when we implement such a the virtual memory, so it's based on the demand paging. Demand paging means we don't have to load the entire program, the virtual memory, user logical memory into the physical memory, because not all the instruction set will be used by the computer. Okay. For example, think about when you code your program. Sometimes for intentionally you put the testing part or something additional function, you should remove such an unused one part. Sometimes it's in your code. It's never been accessed. Also, probably you have something, the flow, data flow, or the logical flow. Okay, then this flow never been accessed, depending on the data or the situation or the condition. Okay, so we don't have to load all of this page, but so whenever needed, we can load such a page. That's the idea of the virtual memory. Okay, or to speed up, even page by page 512 byte is a small size, so we can address the problem of the fragmentation, internal fragmentation and external fragmentation. But what if my module needs 10 of them or the 20, for example, 20, but you have only the 2 or 3 available the pages in your physical memory. Whenever you access this, the module, the part, the unit, find in and out, a lot of pages for it. Okay? So to address that one, if you believe that this part is working together, we can make them do. Okay? So it's a demand segmentation. We will see. So we can increase the performance by grouping the page they are accessed, they are needed, they are called together. Okay? Also, using such a pages, if the certain part of the programs instruction set are shared by the multiple process, we can keep in the memory, so we can allow the sum of the address space shared by multiple process, so we can save the space of the memory. Okay. So nowadays, such a virtual memory swap space used for page swap in and out, not entire. Actually, the swap means the entire the memory space will be swapped out and swapped in, but nowadays it's a page by pages. So then, because of such an idea, so we can increase the degree of multi-programming. Even though we have the limited space, so we can run the multiple program at the same time. Okay. So this slide shows the overview of such a virtual memory. Okay. So this is the physical memory. Okay. Virtual memory means it's your program. Okay. And their data structure is the same. It's a page-based. So pages and the page frame. And we have the map, okay, memory management, MMU unit, okay, memory map is the MMU unit. So using this one, you can map, you can use this one. So what is the data structure of such a virtual address, the memory space? It's the same as what? Actually, the program, process, okay, process, because process is the virtual memory. The process is, what is the process? It's an instruction in the memory, right? So it's the same as you have seen that this data structure is for your process. Actually, when you develop compiler program will design the detailed data structure of the process based on what? CPU type and bus type and computer type. Okay, by considering this one, then this the computing architecture, computing environment allow the, for example, 32 kilobyte the process size. Among them, this code and data it need 100 hexa the address and the heap stack grow this one and heap is this, right? So stack is grow this and the heap is a temporary area. So I think that this is something wrong. Okay, but I didn't check whether virtual space use the different data structure. Okay. I think that I was wrong. Okay, the heap is growing from the, it's a dynamic. The stack is a temporary space. I got confused. Heap is the memory space that is needed for the process, and stack is a temporary space, the parameter value and so on. The stack is from top to bottom, okay? Top to bottom, yes. My mistake. Okay, so that is the same as the process structure. Okay, so this will be assigned when you execute the fork system call, okay? Then in case, not in case, usually many of the instruction set are the command, so we can use such a command area as a shared pages, shared library. So at the time we don't have to load the same pages into the memory. Instead we can share such a memory. Okay. So demand paging, as we have discussed, so we don't have to load entire page to the page frame whenever it needs the command on. Okay. Then at that time we need to manage the memory management unit that can map the virtual memory and the physical memory. Use a program and the physical the page frame. Okay. So this is the this slides for the in this case, so we will use the contiguous. Okay. So this is the main memory. This is your the virtual memory on the hard disk drive space. So swap out, swap in. Okay. Also, we can check whether the page frame is valid or not. Valid means it's the loaded and allowed can be used for the CPU. Otherwise, it's invalid. This is important because from time to time, frequently the page frame will be the page in and out, in and out. So sometimes the certain page area is no longer used, but it's still there. So accidentally, the CPU can, or because of the program bug, it can map get the address which is not valid. Okay. At the time, first you need to check whether this page is valid or not. Because of that, I don't know, I never used the Windows 8, Windows 7, not much, but Windows 95, 98, ME, or 2000, you will see some pop-up memory leak or memory the access error, something like the pop-up message from the Windows that whenever that is kind of a threat, okay? In case you try to access which is not valid, okay? So this is the program, logical memory, and this is the MMU page mapping table, and this is the page frame in the physical memory. At that time, you can see the page number 0. Okay, 0 is the map to the page frame 4. So 1, 2, 3, 4. So it's here. Okay, it's a valid. So only valid the 6 of them. 6 is here. Okay, and C, A, and 5, F here. Okay, and it's a logical view. This will be, you can consider like this one. Okay, so for the virtual memory, so virtual memory it has a A, B, C, D, E, F, G. Okay, then it can be page in and out. So what is a page for? When you cannot find, for example, from the CPU would like to access this logical address is this one, instruction in the page 1. Okay, can you find such a page over here? No, you cannot find the B. At that time, that is called the page 4. Page 4 is the intro, it's a track. Okay, start, then load such a B is loaded into the available space, then set the B is in 1, okay, then change it the value. Okay, then the CPU can access the instruction specific address in the page B. Okay, then the copy this one to the register and operate. That is the page 4. Okay, so this is why shows the overview of such a page 4. Okay, so from the when you try to find it, so it doesn't use what invalid, then the threat, the intro, so it's exception cases, software level, the operating system has such a the module to, it's kind of an exception. Part of the Java program is a threat, is the same as the instruction, but it's a software level the intro. Okay, then copy this one to the page frame and update. That is the process of the in case of the page 4. We already seen such a demand paging. Okay. Okay, so also virtual memory has the other benefit to when we create a process that is called the copy and write and memory map the file. So we will see what is the copy and write. Copy and write is what happens anyway when you create the process. Who create the process? The system code during the kernel mode. So kernel mode, if the system code, the fork is executed, then the current process, which means that it will be parent process will copy. Okay, to make the clone in the memory. Okay, but we reserve the right away the physical memory. No, we don't have to. Okay, at that time, if something right, EXEC is separate because it doesn't share the many of the common area. This will be copy. Does not mean the make the clone does not mean exactly copy to the physical memory. Instead, it has the something the share and the consider only the address. It has only the address. But in case the EXEC then write their own code, then the use the physical memory. It makes sense. Because it's the same, you don't have to keep also. In case something changes, which means write. So copy on write means in case the process write their own the data or the code something, then copy, really copy the process structure. So that is called a copy. Also, when you copy and write, even you need at the time the free space. Okay, free space of the page, free page. So at the time, you can has the something pool for the new process. Pool of what? The free pages. Then you can allocate, use such a pool because to create the process, it takes a time. The users they don't want to wait until process. If it takes 10 seconds, they don't want to wait. So to speed up such a creating process, then the operating system manage certain pool of the free page. Then allocate such a free pages to the creating copy and write process. Okay. So for example, in this case, in case process 1 is write something, because they are shared the many of the pages, okay? In case write something, they physically write their own pages. So that is a copy on right, okay? What if there's no free space, no free pages, no actually free page frames? We need to find, okay? Anyway, one of the physical memory, so one of the physical page frames should be victim. So we need to page out, then use that page. That is called page 4. Page, there will be page in and out. So problem is how to decide which page frame will be victim. Any idea? The simple idea is
Like stack.
first in, first out.
Yeah.
So always the first in, first out. It looks like very simple, but it works. It makes sense also. Because first in means first page in, right? First in, page, which means it's old one. So it deserves to be out. So that's the idea. It's a first in, first out. Not always old is the worst one. Not always. Sometimes the old is the better. Okay? So last in, first out. So you can think about the different way. So we will see such algorithm. Before that, what is the page replacement? Page replacement is the also what is the page itself is the change it. I think that we have seen the same idea, such a dirty page or the invalid page in the database, the memory management, the time. The idea is if a process access the same pages but it's modified, for example, A to B, then instead of the changing the value of this one, instead you can make a copy of this. Okay, then set this one is a dirty page. Then if somebody would like to access this one, then see this is the dirty modified, then find the new one, something like that. This is the page replacement, how it works. Then finally, if that is confirmed, then it will be set as invalid for the dirty pages. Okay, so using that idea, we can see the page replacement. So suppose that we have the two processes. One is the HMJM. Okay, this module is load M, and this is the program counter, which means the current position of this process, and this is the ABCD, another process. Okay, then this is the page table for the first process, and this is another process. So it's loaded. Okay. Then if you wanna execute this one, the one, so
It's like also page table.
so currently 3 is valid, 3 is where, so 3M. It's not, and 4 is 0, 1, 2, 3. So 3 is the H, right? And 4 is the 1. Okay. The 5 is a G. And but M is not here because it's an invalid, right? So it's an invalid. So M is not here. And this one is already occupied. There is no available space. So at that time we need to, this event is called the page fault. Then you need to do the page replacement. Which one? That is the main algorithm of the page replacement. How to decide the victim of this one, because it's a full of that. So M is in the virtual memory. Okay, so you need to page in, but there's no free space. You need to do the page replacement. Okay, approach is you need to swap out all the process, but no longer used right nowadays. Instead, yes.
What does it mean? 15 page, like there's no space anymore?
Yeah, there's no space anymore. You need to decide one of them as the page out. Okay, that page is called victim page. The problem is how to decide. Just randomly select? We don't want to that. What if the J is frequently used, or maybe next time used? We don't have to page out that frequently used page. We'd better page out which is not used, right? That is the idea. But it's not easy to decide whether this page will be used near soon or not. So at that time, we can consider the simple idea is first in, first out. Because it's old, so it deserves to be out. So the key part is how to design victim page. Okay. If we had the free frame, no, we don't have to replace the pages. Once we design such a victim page, so out page out and bring such an page in. So that is the page replacements. So there are different approaches to decide that. Okay, let's see what we have first. First in, first out, which means old one will be victim page, then replace. And optimal, if that is not used for a while, that will be victim, right? So that is optimal solution. The least recently used, that will be victim. That makes sense because it's least used recently. The LRU algorithm. And the most recent page. The most recent page, okay, may be victim. Why? Because it's most recently used, so may not be used, okay. But we don't know, we are not sure. So there are different algorithms. So we will see that one. Also, LRU approximation, okay. So second chance algorithm, they more the advanced. So we will see from the first in, first out. So to do that, we are going to use the two examples of the reference string. Reference string means we simplify the page as the one letter, one number. So one means page number one. So if we have the logical memory unit, which means the process, page number 1, 2, 3, 4, 5. Okay, this is your process, virtual memory. Okay, then first 1 is used. 1 should be used, loaded into the memory. The next 2 will be loaded. 3 will be loaded. 4 will be loaded, and 1 will be reused. The next 2 will be reused, something like that. Okay, that is the reference string. To simplify the problem of page replacement. So each number represents 1 pages. Okay, this is more complicated one. 0 to 8, 0 to 7, 8 pages. So this one shows how many frames. Frame means the physical memory. The more page frame we have, the less page fault. In other words, the more page frame we have, the better performance. Because whenever we have the page fault means what? We need to take out, find the one of them. To decide the victim page, we need to run the algorithm, then to bring the pages into the free page. So it takes a time. So we want the less number of page faults. The number of page faults is kind of the good indicator whether the system is good performance or not. However, even though we have the huge number of page frames, in other words, big memory, we cannot get the linearly increase the performance or the linearly decrease the page fault. It will be like this one. So that means we cannot get the full benefit of this. So first algorithm is the first and first one. This is the kind of the time, okay, from current time to the future. The reference string, as I explained, is a process page number 1, 2, 3, 4, 5. It's a virtual memory. It's your process, not physical memory. Physical memory, how many frames? 3 frames. We have only 3 pages in our physical memory. It's very small. So which means definitely we cannot load entire, okay, the program into the memory because we have only 3 available. So first one, we have all 3 are available at the beginning, right? At the beginning, none of them are occupied. So we can load like this one. Next, 2. Next, 3. Up to this part. The 3, there's no problem. What about 4? Do we have a space? So this moment is called track. Page fault track. It's an unusual case. Did you find the solution for that?
Yeah.
It's a track. Okay. So not always perfect, such as especially for the addressing, disk addressing or the memory addressing, it's not always correct. So if you cannot find a valid one, spread and report to your operating system. And operating system can move to the next. Okay. So it's a page fault. This time it's a page fault 1. Then we have the page 4, 2, 3 in the physical memory. Then CPU need 1. Can you find the 1 over here? No. Page fault again. So which one is the oldest one? Oh, so here, how can we decide the victim page? Because first in, first out. This one is the first in. So will be out. So replace. Page replacement. Then this moment, the 1 is reference, but there's no 1. So we need to find which one is the oldest one. First in. This one is the oldest one. So we can replace this one by 1. So also page 4. Page 4. What about 2? Can you find the 2 over here? No. So this will be oldest one first in, so replace. So page 4. 5. Can you find page 5? No. So this is oldest one, replace. So page 4. What about 1? 1 is here, you don't have to. Okay, you can just refer this one, then use it. Next, 2, use it. So there's no problem. What about the 3? 3 is not. So you need to decide the victim page. What is the victim page? Oldest one. 5 is here, 1 is here, 2 is here. So 1 is oldest one, first in. So this will be replaced. And 4, there's no 4. You need to find oldest one. That is this one, right? So this is page 4. And 5 you can reuse. How many page 4? 1, 2, 3, 4, 5, 6. This is 6 page 4.
Yeah.
9, 1. Because this is also page 4. Because you cannot find 1 at the beginning. So which means it's a page 4. It's not replacement, but you need to anyway bring the pages into the physical memory. This is a physical memory, don't forget. So this is your program, process, logical memory. And we have the page in and out and page replacement in case of the page fault. Okay. What if we have little bit bigger size of the memory, 4 frames? Okay. So we have bigger size, but we will use the same reference string. So 1, 2, 3, 4. Okay, no problem up to this one. And 1 will be reused. 2 will be reused. 5, we do not have 5. Which one will be victim? In first in, first out? First in. So this will be replaced. Page 4. And 1, do we have 1? We do not. So we need to find the victim, that is 2. So this 2. There's no 2. So we need to find the victim. This is a victim. 3? No. So this is will be victim. 4? No. 5? No. How many page 4? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 page 4. Any?
It doesn't make sense.
It doesn't make sense, right? Why? Because we have the bigger size of memory, but more page fault. That is called the delayed anomaly. It's an anomaly. I think that's the name of the researcher, delayed anomaly. Okay. The more page frame we have, the better performance. The less page fault, that's what we want, but not always. Depending on what. Sometimes this reference string. In other words, each pages are referenced depending on the pattern of reference page. Okay? So sometimes it may be happen. So for example, in your program, if you are programming reference previous one frequently, that is a reason. At certain level, you will see a lot of page fault from your monitoring tool, like the task manager. At certain level, you will see a lot of page fault because of such a thing. Okay. Solution? If possible, we can make them do four different ways of page replacement. Okay? Because we don't know which one will be used. If I know the one will be used, I'm not going to replace the one, right? So at that time, you should know such an instruction, the page referencing pattern. So why don't you take a look at this one at home? Okay, it's the same idea. Okay, same idea but different. Page string. At this time, the program is a little bit larger than previous the example. So 0 through 7 is a total 8 pages. Okay, we will use a 3-page frame, physical memory, and the 4-page frame. Okay, you can see. So delay this anomaly like this one. The number of frame eventually it will be like this one. At certain point you may see the abnormal situation. Abnormal that is a delay this because of the the wrong the page replacement algorithm, or you didn't consider the pattern of the page reference. So let's consider more, not always better, but sometimes it's a kind of optimal solution. Okay. So at this time, idea is we will replace which actually this one should be the bold character also will not be used in the future, will not be used for longest period of time. Right? That makes sense. If the pages, certain pages will not be used the longest time among the pages, then that should be the victim. Right? That makes sense. So for example, we apply the same algorithm, same reference string, okay, this one to the with the 4-page frames. Okay, so 1, 2, 3, 4 will be page 4. This one is definitely page 4. Many of the students forgot this is a page 4 initially. Okay, so as you can imagine, this is a good example of your one of the final exam, right? It's easy to make the question and can write down whatever the number is. I can make the all different the question for the student. Anyway, so what? We need to decide the victim page. What is the algorithm? Will not be used for longest time. Let's see, 1 will be used here. And 2 will be used. No, 1 is here, so we don't have to worry about 1, 2. Okay? We can just reuse the existing one. But 5, we cannot find the 5. So, at this time,